The second basic component that defines the pose of an object in the two-dimensional space is the rotation, and thus how the object is oriented in the world. In this case, the problem that we want to solve is to specify the robot's orientation, and so the orientation of the robot's reference frame called R with the respect to the frame W of the world. So, to simplify the calculations, let's assume that the translational component is 0, and therefore the center of the reference frame R matches the center of the reference frame world. To describe the orientation of the reference frame R, we need to calculate the angle theta, which is defined as the displacement angle between the two reference frames. To calculate this angle, we need to apply some trigonometry. Let's start with a fixed frame, the one of the world, and let's assume that there is an obstacle P in the world. And so the coordinates of this point P, by projecting along the x and y axis in the world reference frame, are px, that is the component of P along the x-axis, and py, that is the component of P along the y-axis. In the bidimensional world, these two coordinates are enough to specify the position of the point P in the world. And so, just by knowing px and py means that we know the position of the robot in the world. Let's now draw a new reference frame that has the same origin as the first one, as the one of the world, but this one is rotated. The displacement between these two rotation systems is now expressed by the angle theta, and so the axis y first of the new reference frame is displaced by an angle theta from the y-axis of the world, and the same happens with the x first axis. As we did for the world frame, also for this new rotated frame, let's project the coordinates of P along the x first and y first axis, and with this we obtain the coordinates px first and py first. These coordinates instead represents the position of the point P in the rotated frame. After this introduction, let's now state the problem that we want to solve. Let's assume that we know the position of the point P in the rotated reference frame, and so let's assume that we know the coordinates px first and py first. For example, these have been provided by a sensor of the robot. The question is, how can we calculate the position of P in the world reference frame, and so the coordinates px and py, only by knowing the coordinates of P in the rotated reference frame, and so px first and py first, and also just by knowing the displacement angle theta between the reference frame R and the reference frame W. The px coordinates can be represented as a vector, and we can then project this vector along the x and y axis of the world reference frame. By applying some basic trigonometry, we can say that the coordinates of the vector px first along the x-axis is equal to the length of the vector px first times the cosine of the angle theta. Similarly, the y-coordinate is calculated as the length of the vector px first times the sine of the angle theta. This way, we calculate the coordinates of the vector px first along the x and y axis of the world reference frame. We can do the same also for the vector py first, and so we can project this one along the x and y axis of the world reference frame. Still, by applying the trigonometry, we can say that the component along the y direction is given as the length of the vector py first times the cosine of the angle theta. Instead, the x component is given as the length of the vector py first times the sine of the angle theta. With this new data, we can now calculate the value of px, and this is given as the sum between the vector px first times the cosine of the angle theta and the vector py first times the sine of the angle theta, and since it has the opposite direction, we can use the minus sign. We can make a similar calculation also for py, and this is calculated as the sum between the vector px first times sine theta and the vector py first times cosine theta. This way, we obtained a set of equations that we can use to calculate the coordinates px and py of the point P in the world as a function of the coordinates of the point P in the rotated frame and also as a function of the angle theta. We can also express these equations in a matrix form without changing their meaning. And in this form, we can clearly see that there is a relation among the coordinates of P in the reference frame of the world and the coordinates of P in the rotated frame. This relation is expressed by a matrix that only depends on the displacement angle theta among the two reference frames. And this matrix is called rotation matrix. Back to our example of the robot, we can apply the same concepts we just saw. Let's assume that the robot is able to detect an obstacle by using its onboard sensors, and so it's able to provide its position in the frame of the robot R, and this frame is rotated with respect to the frame of the world W. Therefore, the equation that we ask is unchanged. And so by knowing the coordinates of the person, and so of the point P in the robot reference frame, the one that we called R, and so by knowing the coordinates x, p and y, p, and also by knowing the displacement angle theta among the two frames, which are instead the coordinates of the point P in the world reference frame, we just derived this equation that relates the coordinates in the two reference frames by using a rotation matrix. Let's now move to a practical example in which now we have some real values of the coordinates x, p and y, p, and for the angle theta. And by using those values in the matrix equation, we can see how the only two unknown variables of this equation are the coordinates of P in the world. So, by expanding the product between two matrices, we have obtained the coordinates of P in the world reference frame.